Hello everyone, and welcome back to Reverse Engineering Linux 32-bit applications. In this video, we're going to continue and finally kind of wrap up our discussion of stack buffer overflows. In particular, we are going to talk about something called stack canaries. So what is a stack canary? A stack canary is a value that is put on the stack. It is not a return address or an argument, it's just another value. And this is used to, in some cases, prevent, in others, detect a stack modification. So you might say, well, how does this work? The way that it works is that extra code is added to a function, prologue, and epilogue in order to check for any tampering with the stack. So a canary is a bird. Why do we say canary? A long time ago, when you had mines, they would have canaries or other birds in the mine, and their purpose in there was just to detect gases that might be poisonous. Things like natural gas. Natural gas is actually odorless. They add odor at the utility companies so that you will notice if there's a leak. Otherwise, you would just wind up dead one day or your house exploded and you would have no idea why that happened. So they add an odor to that. So a canary is used to detect a problem. So we use birds in mines. If we look at things like water treatment plants, sometimes they'll have special fish that are very sensitive to impurities in water, and they will use those for a similar purpose. So a stack canary is just something that's added in order to determine if something bad has happened. So the compiler will insert this extra code whenever we have stack protection enabled. This is something that we've talked about when we have compiled our simple examples here. We've turned off the stack protection, and that allowed us to do certain things. Now, there are two common types of stack canaries. There are terminators, and then there are random stack canaries. So first of all, what's a terminator canary? Maybe there should be a movie about terminator canaries. We'll see. Maybe it'd be some sort of combination hacking film / action film. Don't know if Arnold Schwarzenegger would be in it or not. So a terminator canary contains characters that are incompatible with things like stir copy. So here's an example of a good terminator canary. 00, 0A, 0D, FF. So why is this a good canary? Well, stir copy, as you already know by now, will be stopped if you have a null byte. If I'm trying to copy in things and an address or an argument that I want to copy in is 00, I'm going to have a problem. So by putting 00 in my canary, if I try to fix the stack by putting the canary back in place, I will not be able to use stir copy in order to do so. So what about these other characters? Characters like 0A and 0D, carriage return and line feed characters, these will help you block out things like gets that will terminate once you have a new line. Once you hit enter, essentially, they will terminate. So that is why those characters are there. Now, by the way, the order of these characters is somewhat random. I could pick other values. This is just one example value. So if you look online, you might see other people that have examples. They might have these same 4 characters, but in a different order. And what about the FF? FF is treated as an end of file marker in many different situations. So that is a terminator canary. Now, one thing that's bad about this is a static value. So it's a static value. You can easily search on it. And there are ways of getting around this terminator canary. This is something that's been out there for quite a while being a few decades. You know, it's not a bad thing, but in some ways it can actually make things easier for an attacker because they know what they can search for and they can see exactly where a frame ends, etc., etc. And you can easily create the stack, recreate it, and put this static terminator in place. So almost as quickly as they were able to figure out that we had these terminator canaries that we could put in place, people figured out ways around them. So enter the random canary. Now, the idea of a random canary is that it doesn't prevent you from copying things onto the stack. So it doesn't have bad characters like a null, etc. in it. It's just set up so that it is a random value that you can't easily predict. And that value is used in order to detect but not prevent tampering. This is much, much harder to thwart. You are not easily going to be able to predict what the value is going to be if it's truly random, or at least pseudo-random. So it's a lot harder to deal with a random canary. There's some compilers out there that would use a static canary, and it was actually easier to attack than as if they didn't even have it. So how do I attack these canaries? If I have a terminator, I can overwrite all of the data up to the canary. So if I find a problem, if I find an overflow that I can abuse, I can make calls up until that canary. I can change things up until it. And I can point to a new location on the stack. And I can redirect the program. Of course, if my stack is executable, this is the easiest situation. It's not strictly necessary, but if my stack is executable, I can copy a new return address, including some shellcode that comes right after it, onto my stack up until the terminator canary. So I can still do quite a bit of abuse with this situation. What about a random canary? Well, in the Linux world, this is extremely difficult to do. And now I realize this is a class on Linux reverse engineering, but just kind of as an FYI, in the world of Windows, this is somewhat easier. And the reason that it's easier on Windows is that Windows has something called structured exception handling. And you can do an SEH exploit on Windows. How does that work? You tell it, here is where you're supposed to go when you have an exception. We're using SEH, and we inject some shell code into that exception handler. What happens? We overwrite the stack. We overwrite the stack. That is detected by the computer. It says, hey, someone tampered with this. Let me raise an exception. Oops, I'm raising an exception which is handled by malicious code. And that's how you get the exploit. For Linux, you could try to brute force a random canary, but it's not terribly likely to be successful. You have a 32-bit value. You're trying to guess it. You could always try, I suppose. But you're not likely to be terribly successful in those efforts. So that's a random canary or a terminator canary. Yet another way of protecting your programs from stack buffer overflow exploits. So I wanted to spend a little bit of time now and just kind of summarize what we've talked about so far. We've gotten several hours into this course, and we've been talking about stack buffer overflows for a while now. So let me just summarize by saying this. If the user has control of a variable that's passed into a function, there might be an exploit. Whenever a user has control of data flowing into a program, there's the possibility of some sort of an exploit. And stack buffer overflows are, of course, a huge family of vulnerabilities that are out there. So that's why I said a variable that's passed into a function. We will see some other exploits later in this course, but for now we've been talking about stack buffer overflows. So that just requires some sort of a function call with a variable that's passed into my function that I can use and abuse. If I can overflow this variable, I can overwrite the return address on the stack and thus redirect the program execution. I can tell it go somewhere else, not back to the function that called you. And in many cases, I can inject my code directly onto the stack. We've talked about several protections against this. We talked about ASLR, address space layout randomization, where you don't know exactly where this function that you wanted to abuse lives. The only things that you know exactly where they are were things in the program itself. We said the program itself is always loaded at the same address, but library functions are not. This is done by the operating system. So the operating system has this protection built into it or not built into it. Recall that we turned this off by sending a value of 0 to a location in the system partition on our Linux box under proc. So we were able to turn this off. how did we mitigate this? We talked about a couple of techniques. We talked about things such as GOT overriding and dereferencing. Those were some common ways to get around this. You can have a stack that is not executable. This is something that is set up by the compiler. So how does that work? You say, all right, this segment in the program that I'm using for a stack is not executable. It's readable and writable only. And by the way, in general, if your compiler is doing its job, anything that contains code should not be writable. It should only be readable and executable. Anything that contains data should only be readable and possibly writable, but not executable. So if your compiler is doing things properly, this really isn't an issue. So we have a non-executable stack. How do we get around that? We can get around that by doing things like return to libc. We said we could return to other people's functions, essentially. And what do we do if we have multiple things in place? You know, multiple things being non-executable stack and our ASLR. Well, we can combine some of the techniques. Also, with the non-executable stack, we showed you how you could chain together these return to libc calls. And then finally, in this video, we talked about stack canaries. We said, how could I get around a stack canary? So hopefully by now you've learned how is it that stack buffer overflows exist? How can these problems creep into software? How can I detect these problems and how can I exploit them? And you'll see that on the Linux platform, this is pretty hard unless someone has explicitly compiled away some of these protections or disabled things like ASLR in the operating system. What you'll find is that the Windows world, especially if you're dealing with older versions of Windows, is far easier to exploit these vulnerabilities. It's not impossible with Linux, it's just that you have to work a lot harder in order to exploit this stuff. Well, that pretty much wraps up our discussion of stack buffer overflows in the 32-bit Linux environment. We're going to go on from here and we're going to talk about some other common vulnerabilities that you can find in software. But that's all for this video. As a reminder, this video is one in a family of videos in all things InfoSec that you can find here at Pentester Academy. And I look forward to seeing you in this course or another course soon. See you then.